we're going to talk about how to create your own refactoring tool with Clang. And this was just kind of a placeholder for all the things I wanted to talk about. Here's the real problem. There's just a dearth of refactoring tools for C and C++. The existing tools are also tightly coupled to specific IDEs. Visual SysX is a good example. It's got some nice functionality in it, but if you're using Eclipse, can't use it. If you're using Vim, you can't use it. So the tightly coupled to an IDE problem is a significant one. C and C++ code bases are often old. And I don't know why. Something about the culture of C++ with a focus on code that is very concrete and intimately connected with bit twiddling, if you will. There's something in that culture that tends to generate code that is like long methods full of lots of details and multiple responsibilities jammed into the same class and things like that. The code's in desperate need of refactoring, but it's so dangerous to do manually that people are afraid to refactor their code, especially if they don't have any automated tests to let them know that they've messed things up. And I sympathize with that. So I think the answer is automated, high-quality tools that you can trust, and that trust is really important. How many people here have some kind of environment where it wants to guess ahead of what you're typing and like automatically suggest things and automatically fill things in? How many of you turn that off? Why do I turn it off? Because it's not helping me if I'm typing correct code and you automatically complete it to incorrect code. Nothing should ever take correct code that I'm typing and change it to incorrect code. And it's the same for a refactoring tool. A refactoring tool, when applied to your code, should never ever require a manual edit after you're done applying the tool. It should never take correct code and turn it into incorrect code. But the existing tools that are out there, because they haven't been based on a production quality language parser, are more heuristic based, and they just kind of like, oh, I'll just search for some curly brace and then put some stuff in there. And even what I'm going to show you today has a little bit of heuristics in it that I would like to figure out how to get rid of. I have a suspicion I can, but I haven't gotten that far yet. So C and C++ code bases are often quite old, and the older the code base, the more desperate is in need of refactoring, but we need automated high-quality refactoring. And to get some kind of tool adopted into everybody's workflow, it needs to be easily invoked from your workflow. That means if you're in VI, I should have a way to invoke it. If you're in Emacs, there should be a way to invoke it. If you're in Visual Studio, there should be a way to invoke it. If you're in Eclipse CDT, there should be a way to invoke it. If you're in Qt Creator, should be a way for you to invoke it. The tool has to be accurate, and it can't ever produce incorrect code, or you just won't use it. You just go back to doing manual things. So here's some examples that I know of that exist. If you know of more, please email me, because I always like to hear about other refactoring tools. I am willing to go try them. I currently develop in Visual Studio because that's the environment most productive for me, but if I had something that was giving me really powerful refactoring, I'd probably switch. There's Visual SysX and CodeRush are two add-ons for Visual Studio. I use Visual SysX. It's not bad, but it still has a tendency to change my code and kind of do half the job, and then I have to go do the other half with a manual edit. CodeRush is one that supports a lot of refactorings, but when I last evaluated it, maybe I guess it's getting on 5 years ago now, it was just too buggy, and it just slowed everything down. I mean, scrolling the source window got slower, and I'm like, why is my down arrow key suddenly working so slowly? From the CLI, there's several tools that are provided in the Clang distribution. There's Clang Modernize. There's remove CStir calls, which we're going to look at in more detail. And Clang Tidy, it's a refactoring tool, but it's more along the lines of we have this rule that says all our member variables have to end in underscore, and this one doesn't do that, so I'll just fix it up for you. It's more those kinds of style-based refactorings. The Eclipse C Developer Toolkit version has some refactorings. Every person I know that's ever used that says they suck. So if you know of other ones, please email me, let me know. So here's an example, the problem we're going to look at today. We've got this source file, and the thing that is in here is that some guy with dusty old C habits has been putting useless voids in all the empty argument lists, and we think that's stupid and just a complete pointless distraction, so we want to get rid of that. And that's the tool we're going to build. So, but it's more than just function signatures, right? I mean, here's all these pointer to functions and pointer to member functions and type defs and static casts and reinterpret casts and C-style casts and return values of functions that return function pointers. All of these places have this little extra void in there that we want to get rid of. So the way we're going to attack this is going to use Clang, the tooling library that's in Clang. And I develop on Windows, so I went and downloaded the binary package, and nothing's there. No libraries, no headers. It's in the Linux package, it's not in the Windows package. So I had to go and build the whole tree myself. I built it on this machine, which has 8 cores. I generated like enough heat to pop some popcorn, and it took 90 minutes of 100% CPU, and I got a 9 gigabyte build tree. Okay, that is not a really workable situation. We'll see what we're going to do about that. And it's like, seriously? Yeah, that's what you're stuck with if you want to develop a refactoring tool in the Windows environment for now. The Linux packages have the headers and the libraries, static libraries. So you could get going with a Linux pre-built package. But you may not have a Linux distro supported by this package. You might have to build it anyway.
What compiler did you use? Because I did use
Visual Studio, but it's not a matter of the compiler. In terms of the package that they've built, it's not a matter of the compiler. It's a matter of the way they're building the package. There's support for it in the build system to make an appropriate package. They just, for whatever reason, told the build system not to. Because I think they had in mind like that Windows was some weird use case that wasn't like all the other platforms, which I think is wrong, but that's why they built it that way. They intentionally did this, left it out of the package. There's also, some of the packaging logic is missing some useful tools for a refactoring developer. We're going to look at one of those tools that is missing in the 3.4 distribution. There's also that tool we're going to look at required libedit to be built, and libedit was just window dressing. It wasn't a core need of the application. It was just to give you a nice scroll back history of command input. I hacked it on my Windows machine because I don't have libedit to work without libedit, and that will be what I'll be showing you later. And I don't know about the build. I've got a bug open on that. Some of the tools being missing, it's gotten a little better in 3.5, which has not yet been released, but that is what trunk is. And because I went to go contribute some of what I'd done here as a patch, and I was like, oh, they're moving so fast, they already fixed it. So it's getting better, and whatever is that I think is missing that would be useful to a refactoring tool developer as a pre-built binary included in the package, I'll be submitting patches back to them to try to get those things included. So that's basically what we said here. It should be better in 3.5. My goal is that you should just, you don't, as a refactoring tool developer, you don't actually care about building Clang. You care about using Clang as a library. So you'd like to be able to just download something that has the library built that you can just link against it, has header files, has documentation, so you figure out everything you need to do, but you don't need to be, a Clang build expert. And that's the goal that I think we can get a lot closer to that in 3.5. So here's what we want to do. We need to remove this void paren stuff. There's an existing refactoring tool shipped with Clang called remove CStir calls. And that thing removes redundant calls to CStir. So if I have a method that takes a standard string and I pass it a character literal, there will be an intermediate temporary created that is the standard string that holds that character literal, and then that's what the function sees, right? But if I have a standard string and I call CStir on it to get a C-style string, and then I pass it to that function, I'm needlessly taking my standard string, converting it to a C-style string, just to create a temporary of a standard string holding the C-style string that I can then pass to the function. So there's needless work going on there. What remove CStir calls tries to do is identify functions that receive arguments by standard string, but the actual argument that we passed it was a standard string on which we called CStir, and then it just removed the CStir. So we can use that tool as a starting point. Here's an example of what this tool does. Here's a call to a function that takes a standard string, but we've passed it the CStir result of a standard string. Can you guys see that?
No, not really.
Sorry. It's just too bright from that. Oh, the doors open out, so that'll work. Guess I'll have to go past the shades. All right, so that's, can you see it now, or is it blurry?
I have trouble seeing blue on dark blue on dark backgrounds.
Well, it's cyan actually, so it should be bright. But anyway, it should be okay as we. Is it easier to read this stuff in the box?
No, that's harder to read.
That's harder to read.
Yeah.
Wow. Okay, I screwed up on my color scheme. Anyway, so we're gonna remove that. This tool will remove that call to CStir, and so let's take a look at how this code is put together. The first thing, as if you opened up that file, the source file for remove CStir calls in the Clang distribution, the first thing that's interesting you'll see is there's a couple of command line arguments. LLVM support library gives us a class for handling command line options. The first positional argument in the command line to remove CStir calls is the path to your build directory. And then there's one or more source files. And in their implementation of main, there's some startup code that the first thing they do is just call a function to print out a nice stack dump if they got an unhandled signal. They create a compilation database, and we'll see more about compilation databases. And parsing the command line options, and if we didn't get a command line database when we first tried to get one, we'll try to parse that out of the command line options again. We'll try to load a command line or load a compile database from the build path that was specified. And if that didn't work, we're going to throw an error, because you can't do anything useful with the refactoring libraries in Clang unless you can supply it a compilation database, and we'll see why in a bit here. And then the very last part is that we're going to instantiate this refactoring tool, and Clang has already a small class hierarchy of tools. And a refactoring tool is a base Clang tool that knows how to parse source files into an abstract syntax tree, match nodes against that abstract syntax tree, and then create a list of source file text replacements, and then apply those replacements to the files and save it out. And you build this tool, this refactoring tool, from a compilation database and a list of source files that you're going to refactor. So the main thrust of any one of these kinds of Clang-based refactoring tools is that we're going to have a match finder that is the thing that connects up our code that figures out what kind of replacements to build, connects that to a syntax tree matcher. And here's, in this particular tool, fix CStir call is the thing that implements that callback on matched AST nodes. And we connect it to the tool by using, it connected to the tool has a replacement list that it will use, and we connect our little code that's going to identify the code to be replaced. We connect it to the replacements list. There are matchers added to the finder. We'll see in a second what the detail of a matcher looks like. And then the tool, you call tool run and save. And that basically just, everything up until this point has been just kind of wiring components together, and then we say go. And it's kind of nice because notice like this saves us from having to figure out like, well, you know, I got to go open the source file, I got to go down to the point where the source text is located and put in the replacement, and then I got to put the rest of the file out there. And what if I have lots of edits to the same file? I got to make sure I do them all in the right order, or I might mess up something. And the tooling infrastructure just handles all of that for you. So all you need to worry about is writing the code that says, what am I looking for in the abstract syntax tree, and what am I going to do to it? So you stay focused on writing a refactoring, and you don't have to worry at all about any kind of file system saving and any of that stuff. So here's this remove CSTR calls has two matchers. The first matcher is this one where we look for something that is a function that takes a standard string, and we're passing it a standard string where we've called CSTR on it. Let's take a look at these little pieces in here. Matchers are built up with this Fluent API that basically gives you a bunch of methods to have a readable source code that says what kind of matching construct you're building. A construct expr, all these matchers have names that match the class names of the abstract syntax tree. So in the abstract syntax tree, there's a C++ class called construct expr that represents expressions of constructors. Because what we're looking for is constructing a standard string from a call to standard string.cstr. So we're looking for a constructor call expression, and the constructor call should be declared with the same name as the string constructor for standard string. It should have an argument count of 2. That is, the constructor should have an argument count of 2. And the first argument should be a call to standard string CSTR. We figure that out by using a member call expr because CSTR is a member function, so invoking that is a member call. And we can bind any of these nodes to symbols so that when we're processing the match nodes, we can query them by symbol name to find the appropriate part of the match. There's a bit of code in the handling of the refactoring in this tool that tries to differentiate between when you say string.cstr or you have a string by pointer or smart pointer and you say string dash greater cstr. And in order to figure that which one of those cases out, it needs to have a binding to the member expression. The member expression is the part before the function call arguments in the case of a member function call. And so they just bind that up so that they can use it later. And they say that the member call that we're matching against has to have the name, has to be declared with the name of the string CSTR method. They also going to want the argument to this member call, so they're binding that up. And these call-e matchers, the inner matcher, in the first case it's member expr and then method decal. They match up between the actual call and the call-e. It's the call-e that we want to match against. And then the second argument should be the default argument. Because if you remember, standard string takes an optional second argument that I believe is the allocator, and we just don't want to deal with allocators. We're going to assume that that argument is the default. And then finally, attach it to our processing code by take this whole thing, that whole first part was building up a matcher, and then the second argument is our callback code. The second matcher does something very similar, but it's for there's some string classes that are internal to LLVM, and this refactoring tool is used on the LLVM and Clang code bases, and so they want to do the same kind of fix-up when people use their internal string classes. And in this case, it's a method decal, but it could be one of two different constructor names. So would they use any of to combine them up? In general, these matchers, there's this rich, fluent API for building up matchers, and there's the ability to say an outer node takes an inner list of matchers, and all the inner list of matchers, if they all match and the outer node matches, then the whole thing matches. It's just a way to combine things up without having to write lots of code to do it. Any of takes a list of child matchers and matches if any of the child matchers match, which is just saying if it has either of those two names in the method declaration, then the method declaration is matched. And in this case, they don't have that second default argument, so the argument count is only 1. And these are the method name constants. You know, standard string isn't really standard string, it's just a type def for standard basic string of char and char traits of char and allocator of char. So that's the real name that we have to use when asking, is this constructor have a declaration that matches that? That's the name of standard string, and then the method name is basic string, because it's the constructor of basic string that we really are interested in. It's the same deal for CStir, that big, long, disgusting name of what standard string really is, and then it's the name of the CStir method. Yes?
So what if you wanted to map, say, wchar string, right?
So wstring?
Right, so...
You would need to just duplicate all of this same stuff,
and then use
and you would use standard basic string of wchar. Sorry, repeat the question. The question was, what if you're using wstring, which is another type def of standard basic string on wchar instead of a type def on char? And it just means that these names would change. You would, because the refactoring that we're doing when removing these calls would work identically for wstrings as it would for narrow strings. So you would just need to, as we did for the Clang LLVM string classes, you would match on a method name that was any of narrow string constructor or wide string constructor.
Does the tool have a way to match any template, right? So you could just use T instead of char.
So the question was, does the tooling infrastructure have a way of matching any template? And the answer is yes, but not when I'm referring to specific names of specific instances of a template. And the only reason that I'm stuck with handling only narrow strings here is because I referred to the method by its name, and I'm referring to the method of a particular instantiation of the template, and in other words, I'm not refactoring the template definition, I'm refactoring instances of the template. Does that answer for you? Okay. So we're going to cheat and take our refactoring tool and just stick it down in the Clang distribution as the easiest way to get going. And so we'll do that by copying this remove CStir calls into a new directory. We'll copy their source code and rename their source code to be a file name that's suitable for our tool. So we'll rename CStir calls CPP to remove void arg CPP. And we will edit the build script cmakelist.txt to change the names again, make them match. And then we'll edit the parent directory cmakelist.txt to traverse into our new subdirectory that we've added. And then the code's exactly the same. It's exactly the same thing. It's just under a new name. just test the build to make sure that we got it glued into their build correctly. And here is our little test case, our first set of test cases. This is one that we're interested in that has the void argument. This is the one we want to change. Here's a function that has no arguments but didn't have the void. That's related, but we want to leave that one alone. And then here's one that takes an integer argument. We want to leave that one completely alone. So we just kind of put some simple variation in there to try to get things going. Now, what's nice about Clang is that you can dump the abstract syntax tree just from the command line. And we can do that by passing xclang, astdump, -f syntax only, and the name of our source file. It will then parse the file and then dump out whatever the abstract syntax tree that it found in a little kind of pretty printed tree style representation. And this works just fine on Windows even, so you don't need to run the Microsoft compiler to get anything going on here. This is just pure parsing and then building an AST and then dumping out a representation of the AST. Every abstract syntax tree that you're going to process is almost certainly going to start with a translation unit decal. So that's a declaration record that in the Clang AST model that represents the entire translation unit, everything in your source file. Here's our first function that was interesting, and it was turned into a function decal nested inside the translation unit decal. And over here we can see that it said, oh yeah, and the function is named foo, and its signature is int with a void argument list. And it also tells us the source location of all of the things that it found in the abstract syntax tree. So every node in the tree is associated with a range of bytes in the source file, which is great, right? Because that's exactly what you need for a refactoring tool. You need to find that stuff in the source file. In this case, it says it's in test CPP, line 1, character 1, to line 3, character 1, which if we look back at our file, that I'd actually in my little test file, I didn't have that comment at the top, so it starts right at line 1, character 1. The next function decal, it finds bar and it says int with void parameter list. We'll get to that in a second, why that one also said void. And the third function decal that we had in our file was a function called feasel that has signature of taking an int, returning an int. So it found both our argument list functions, but it printed them out both with a void argument list signature. So what's going on there is that when you dump out the abstract syntax tree and it shows you this little summary of each node, it is printing that in what it thinks is a canonical form in terms of just how these abstract syntax trees print out a summary of what their contents are. So it's not literally text from your source file. It's a representation of the syntax node that was built from the text in your source file. So in Clang, building these matchers is kind of the essence of how you get at the pieces that you're interested in. There's 3 kinds of matchers that they have created. You can create your own matchers as well. The first type is a node matcher, which matches to a particular kind of node, like a constructor declaration, a field declaration, a variable declaration, so on. Then there's narrowing matchers that match on the attributes of a node. And we saw an example of that where we were taking a matcher for all constructor calls. We narrowed it by saying that the constructor calls declaration name should be the constructor for standard string. We narrowed it further saying it should be the constructor that takes 2 arguments, and then further that the second argument should be the default argument. Those are all narrowing matchers that were added into the node matcher to focus that match down on just the constructor calls we were interested in. there are also traversal matchers that allow you to express more complicated matchings based on relationships between nodes. So in our example, we saw an example where they used the callee matcher, where they were matching up between the caller and the callee. And you can use that to do parent-child relationships and all kinds of interesting things. So there's a matcher reference on the Clang documentation website. And when I first looked at this table, it's a lot longer than I've shown you here. This is just an excerpt of the node matchers. But when I first looked at this table, it was a little confusing to me because these links don't actually take you to the doxygen for the matcher classes. They take you to the doxygen for the abstract syntax tree nodes that the matcher classes match. So basically, to understand the matcher classes in terms of the documentation on their website, it's this one page. And you have to figure this out. It's the center column is the name of the matcher function. The right column is the types of the matcher arguments. And I don't know if you can see it clearly, but there's a little ... there on some of these command line arguments. And that means you can have one or more, or 0 or more arguments of that type. And then the matcher generates a type that is matcher parameterized on some node type. And then the key thing that's not obvious is that the types that are returned by the matchers are the input types to other matchers. So to figure out what combinations are possible, you kind of has to keep looping back and forth between the left column and figuring out where you can use that on the rightmost column. Once you kind of get that mental map, you can kind of see it's still not as easy as it should be. I have some ideas about that. But you can. This is how you have to traverse this table in order to build up more complicated matching expressions. Each matcher has doxygen documentation for the nodes that's linked from the matcher reference page. But almost all these matcher functions are really simple expressions, and they live in a single header. So you can just go, it doesn't hurt to just go and look at that header and see, like, oh, that's what it's doing. It's calling that member function on the node and comparing it to this value, and that's how that thing is doing narrowing. So I mentioned there was this thing about a compilation database when we were talking about the command line arguments. One of the difficult things of refactoring C++ code is we have to know the entire preprocessor context up to the point that we are refactoring. So that means any symbols you defined on your command line, I have to know the include path that you're going to use to build this file, because different preprocessor symbols could be defined depending on whether you've got the debug directory searched first or the release directory searched first. Lots of interesting and creative things people do with their build to control how symbols get defined, and you have to manage all of that. The way that Clang for the refactoring tool infrastructure has decided to support that is to use this thing called a compilation database, and it basically contains the full compile command for every source file that you build. And it's just a JSON array of objects containing 3 attributes on each object, the directory containing the source file, the command line used to compile the source file, and the source file name. And CMake can generate these. Yay! But not on Windows. Boo.
Really? Not on Windows?
Yeah, it doesn't work on Windows. I don't know why. We think it's just missing implementation, that they were just too lazy. There's been some discussion on the Clang mailing list where they said, really the right way to do this is to get CMake patched. And I think someone is working on that. Okay. And if they're not, then I eventually will. Because I develop on Windows, I'm fixing all my own pain, right? You know, that's what I'm doing. But in the, you can get these JSON files by just typing them in an editor, and I'll show you one in a second. And I actually came up with kind of a hacky scripty way to process the Visual Studio build log to get it generated for a large build system.
Well, could you just write your own build system that used this build compilation database to do your compilation for you?
I don't actually know anybody. The question was, can you have a build system that uses that compilation database and uses those commands to do your build? I don't think there's, even in places where the compile commands JSON gets built, I don't think that's how it's used. It's only used by Clang to know, it's used by Clang to decouple Clang analysis from your build.
Okay.
So your build system records the commands that it uses to build source files. Clang can consult that, but Clang doesn't need to know, is your build scons, is your build CMake, is it Makefiles, is it Visual Studio, is it Xcode?
Okay.
And so what does this look like? Here's an example of one. I found that things would go horribly wrong if I did not use slash for the path separator. I could have done the doubly disgusting thing of doubling up all the backslashes. The problem is it's a JSON string, and a backslash is a string quoting character in JSON strings, right? So if you don't, the easier thing was just to make it more legible by changing the backslashes to slashes. So that's the compilation database. That's all pretty much clear to all of you guys, I'm sure, right? Why you need that. So let's get on with making our refactoring tool. We're going to, that simple test CPP, we're going to see if we can get some things matching in there. And so here's our tool, fix void arg, and we're going to build it just like we built fix CSTR calls with a reference to the replacement list, so our tool can add to that list. And here's our simple matcher. We're going to look for function declarations where the parameter count is 0 and bind that to a function, or to an identifier called fn. And our refactoring tool, there's some basic stuff that every one of these tools is going to need to do. It has to implement the match callback protocol. So we do that by just deriving from a base class. And it has to remember the replacement list. So we just have a private member variable that we stash things off in our constructor. And I imagine that this little piece of boilerplate would be the same no matter what kind of refactoring tool you were writing. Here's the more interesting part. And so every one of these refactoring tools has to have an implementation of this virtual method called run, and it receives a match result from the nodes that were matched. So there's some tooling infrastructure that's run the parser against the source file, built an abstract syntax tree, taken our specified matchers, matched it against the nodes in the syntax tree, and it found some matches. And so by the time it gets down to the code you write, it's like, okay, here's some stuff that matched. You go do whatever you want to do with it. And I just made a local variable here for the bound nodes. The bound nodes are the nodes that matched that we bound to some string identifier. In this case, we bound it to fn. And their source manager is the thing that connects your nodes and their source locations to files on disk. So we are asking the bound nodes for a function decal node that was bound to fn, because I could bind function decal nodes in many different contexts to different identifiers, and I could pass them all to a single callback. So in this case, we're just looking for the fn. And there's a little function, it's maybe 10 lines long in remove CSTR calls that, given a source manager and a node, an abstract syntax tree node, it gets the starting location of that node and the ending location of that node and gathers up all the text represented by that node and returns it to you as a string. That function isn't particularly interesting. It's in the source code if you want to see it. but that's how we get the text associated with our node. And then we're going to do something heuristically. This is the part I'm not particularly happiest about. I think there's a better way to do it using the syntax tree directly, but this was easy and quick enough to get me going. But I don't like it because it's a heuristic. It's not really parsing. I'm saying, remember, this is a function definition, so it's the whole function, including the open, close curly brace of the function, the whole body of the function. So I just go and look for the first curly brace, then go back to the last right paren, and then I say, okay, that's the part where my function declaration ends. Now, of course, this obviously is a heuristic and not the greatest, but it gets us going. And then if I found some declaration and it ended in paren void paren, then I'm just going to print out that what I matched. And I have another little helper function that I wrote here that, given a syntax node that is in the tree, just uses source manager to go and find its file name and location and print, return that to me as a string so I can print that out. So if I run it on this little simple file, what I get is it found on line 1 in test CPP, it found int foo void. Great. So we're finding exactly what we're looking for. But this is not a realistic test file at all, right? So what happens if we put an includes cstandard.io at the top of our file? So put include cstandard.io at the top, run our tool again, and it matched a whole bunch of extern C functions that well, first of all, I don't want to refactor those because they're not mine. And secondly, extern C functions, I'm not sure I think it would be okay in C++ to apply this refactoring to any functions declared extern C, but remember, the best quality of a refactoring tool is one that is reliable and does not produce incorrect code. And if we're not sure, then don't go there. You can always extend it later after you do some analysis and determine it's okay. I think it would be okay, but we're going to be conservative and say we'll just ignore all those.
The problem comes, it's in standard.io.h. The problem comes is if your implementation of the C standard library is also used by a C89 source code and compilation elsewhere, then you're going to break those because you're going to disable.
Well, I certainly don't want to refactor standard.io.h, right? I mean, I'm not the owner of standard.io.h. But the easiest way to just get all of this off our plate is to check for functions that are extern C. So we can do that because there's a little predicate method on the function node object that says, is this function an extern C function? And we can just say, if it is, just return. Don't do anything. Don't want to care about those. So that gets us back to identifying our single one. Yes?
Is there any way to tell whether that came from an include file or from your source file?
The question is there any way to tell if this matched node came from an include file or my source file? And the answer is yes, and we'll get to that in a moment. The answer is the source manager knows the source of everything, which is why back here, when we printed out the location of all these matches, it knew that it came from standard.io.h on a particular line. I got that from the source manager. Okay, so what about declarations of functions taking a void argument list? If we add a declaration to our source file for foo, int foo void, and we run our matcher, it found the definition, but it did not find the declaration. So we need to do something a little bit more in our matching or in our analysis. Got the definition, did not get the declaration. So there's another method on function, the function node. It's actually function decl node. My local variable is called function. That says whether or not this declaration is a definition or not. So we can use that, and we can say if it's a declaration, then let's print out that we matched a declaration. If it's a definition, let's print out that we matched the definition. So once we do that, it says, hey, I found one declaration on line 3, and the declaration was int foo void. I found a definition on line 5, and that also had int foo void. Yes?
I'm curious, if you didn't fix the declaration, would the compiler complain later?
No,
Interesting.
because the question was, if I did not fix the declaration, would the compiler have complained? And the answer is no, because semantically, paren void paren is identical to paren paren, which is why the extra void is just a distracting nuisance. Okay, because it adds no additional information, it conveys no intention, it is a completely equivalent to paren paren. So we can now, now that we've identified the things we're interested in, we can start doing replacing. Because it's just string substitution, right? So we'll call, we'll just get the substring of our, and this one is the this is the declaration. So we'll strip off the void paren, replace it with paren, and then we'll build a replacement. A replacement is built from a source manager, the AST node that we're going to supply replacement text for, and the replacement text. So in this case, the node was the declaration, so I just needed to supply the replacement text for the declaration. And after you've built that replacement, you just insert it on the replacement list that you were constructed with. Same thing for the definition. The only wrinkle here is that because it's a definition and not a declaration, we have to make sure that we don't accidentally delete the body of the function. So it's replace some stuff in the middle and then keep the stuff on the ends. Yes?
So I'm going to be really picky here. Let's say that you had the line int slash star paren void paren star slash function name paren void paren. Would that have replaced the comment? Or does the comment not even make it into this because the IST doesn't even have comments?
Okay, so the question was that suppose I had this written as int foo open paren open comment void close comment close paren. Comments are not members of the syntax tree, right? Because comments are white space. So in that particular case, you'd have to hook in on at like the preprocessor level or something. By the time you get an abstract syntax tree, the comments have been removed. But when you do replacement, you have to be aware of that. But like when I replace the function body, the text, the source file text associated with the node does have the comment in it. The abstract syntax tree says you have a function call or a function definition that has 0 arguments. You could notice that the source location of the open paren and the source location of the closed paren had a gap, and then probe into that gap by obtaining the text from the source file between those 2 locations, look for this comment and get rid of it.
Well, that's my question then. Would the replace insert, is it searching the source or is it searching something else? Is it?
I'm doing a string replace on the source.
Okay, so
The source code associated with the node. But when I queried the node for matching purposes, the comment didn't enter into the matching.
Right, but so if
But it is here, yes.
if the comments were there before the signature, you would be replacing the comment and not the signature.
Not here, because I look for the thing that is in telling me to make the change is I said, did the declaration or the definition end in paren void paren? And in that case, it doesn't. It ends in paren open comment void close comment paren.
No,
Yeah, but if you had open paren, close paren, and then had the comment where paren void paren.
Right. Put the
comments.
comment between, say, between the int, so you have int f void close paren, right? So say int comment void paren close comment f void paren. You would be replacing the comment on the source line and not the actual code. I know I'm being,
Possibly as the way I've written this, but the answer is no, not the way I've written this, because I am stripping off the last 6 characters of the source text and replacing that with paren. So in what you just described, it wouldn't be the last 6 characters.
Right, I mean, it sounds like there would be a mishandling of that scenario, not quite the mishandling described. Maybe I think you would just miss it because of the way you were searching in the text.
Yes, so remember, we're starting with simple cases. The question was, could I present some torturous input to this code that would make it do something wrong? And the answer is yes, because we are starting with simple cases and working our way up to more complex cases. But this is a very good point that, there's nothing that says you can't have comments and other white space between tokens. And this algorithm, as I'm showing you, is a little bit heuristic because it's doing some string compares. And, for instance, it's looking at paren void paren. It's not doing a strict token analysis. So the answer is kind of yes and no. We'll see an example at the end here where you might think, based on what I just said, that if I put any kind of arbitrary white space around the parentheses or the void or whatever, that my code would fail, but it in fact does not. And it has to do with, remember I said when we dumped out the AST that it had that canonical way of representing things? It comes back to that. Okay, so do the same kind of string replace on that, and we run it on our test source file, and hooray, the little paren void paren got removed from the declaration of foo and the definition of foo. So we have, with a small amount of code, we just wrote something that does a refactoring. And it's automatic, it's reliable, it does not produce incorrect code. Has all the qualities that we like in a refactoring tool. So what do you do from now on? Well, you do the shampoo algorithm. Lather, rinse, repeat. Write matchers for the next thing that you want to match in the syntax tree. Build replacement text for the things that you've just matched. And keep iterating until you've accumulated all the constructs that you want to handle. It was mentioned before that we were matching. Yes, this question.
It's just on the slide where you showed the output. I noticed it's missing all the new lines that were earlier.
I just deleted some new lines to get it on the slide.
Okay, I just wanted to make sure.
I will show you a real example of we'll run the tool and then we'll look at a diff, and I think any white space paranoia will be alleviated at that time. But it's a fair point. Again, just because I run a refactoring tool, I don't want it changing all my indents or anything like that. So this is a good time to digress a little bit. You guys, how many of you guys are familiar with Clang format? About a third. So Clang format is actually a tool that they created as a consequence of their attempts to create refactoring tools. Because they were making refactoring tools, and we deleted some characters from a line. What if at the end of that line, somebody had created that nice little kind of column of comments all lined up just right? Now I deleted 4 characters off the line, and damn it, you screwed up my columns. Clang format is designed to make that person happy. Because Clang format can be instructed with all the particular little style rules that you have. And after we refactor code, we can run the Clang format pass on it, and then Clang format will say, hey, looks like all these things used to be lined up in a column except for this one, so I'll just fix it for you. And it'll put in some white space. So that is another thing that as a refactoring tool author, you don't have to worry about. If someone says, hey, I ran your tool on my thing and it just moved all my white space around, you're like, dude, just figure out a Clang format configuration that works for your code, and either run it yourself on your code after you refactor it, or I'll add a feature to run Clang format with your format style after every time I change your code. But it's another thing that the tooling infrastructure does for you that you don't have to worry about. And trust me, the details of elaborate formatting is not what you want to spend your time on. You want to spend your time on improving your code with an automated tool. Okay, so lather, rinse, repeat. That's what we're going to do. At some point, as was mentioned earlier, you get matches against files you can't change. And we need a way to, like I actually ran my tool against, or I looked for instances of paren, void, paren in boost, and I found one at boost scope exit. But I don't want to refactor boost just because I included it. I just want to refactor my stuff. Visual SysX has something like this where it says, tell me all the directories of things I should never change and I should just assume are stable, so I don't keep rebuilding indexes and stuff like that. And I think it's a good idea. So the source manager knows the source file of everything that we're editing. So I just made myself a little Boolean predicate that said, go get me the source file associated with some source location. And if that thing was test CPP, then okay, we're good to go. Now again, simplistic logic, because we're doing the simplest thing to get us going. But it's not hard to figure out how to handle this, to handle arbitrary directories and search paths, blah, blah, blah. You know, that's all just details. It has a nice little method on Source Manager called getFileName. You give it a source location, and it gives you back the file name. It gives it to you as an LLVM string ref class. You can call stir on that to get a stud string out of that. It's kind of annoying to have to keep writing a matcher, compiling it, dumping out the output to see if we matched nodes. There's a tool that comes with Clang called Clang Query. It is not in the 3.4 package, but it is in 3.5. It will be in the package. I already checked that. And this is the one that was dependent on libedit, and so I had to hack it up a little bit to get it to build on Windows. But they've also fixed that in 3.5, so that'll be fixed. And you just run it with a source file. It has some other command line options too, and you can. It'll get the compile commands JSON from the same directory as the source file. For my testing, I built my compile commands JSON from my Visual Studio CL command line. So I passed all these command line arguments to Clang that it's like, I don't know what to do with that. You know, all these kinds of things that complained about, but they're all just warnings and it's harmless. It did parse my source file and turn it into a source tree. And from there, I can run a match command where you just express arguments to the match command that are the names of those matcher functions that we saw on the AST matcher reference. So I can say match static cast expert. This is a later version of my test for source file that has some static cast stuff in it. And then it said, hey, yeah, I found a call to static cast. And it puts a little green arrow at the beginning of the source location that matched, and it puts green tildes spanning the range of source text that matched my matcher. And in this case, I said match a static cast expression. So that's everything beginning with static cast all the way to the closing paren of the static cast. Note very carefully, it does not include the semicolon. So when I run the matcher and it gives me a range of source locations, if I had lots of white space and comments and all kinds of crazy stuff sprinkled in there, the beginning and ending source locations for the matcher would span that entire range. So we can take a look at Clang matcher or Clang query. I need to do duplicate. There we go. You guys can see that? So I can start it for you again. I've got my test file. This test file has a lot more stuff in it. So I got things with white space and function pointers and member function pointers, all kinds of crazy, disgusting void stuff. I can query on that, and if I say match static cast expr, those are the matches we got out. If I say match function decal, here's all the function decals that it matched. It's 337 because I wrote custom code in my refactoring tool to exclude system includes, but Clang query doesn't know anything about that. I think actually that is a very common use case, and I might contribute a matcher back to Clang that allows you to say a matcher based on the file name associated with the node, so you can just discard all the ones except the ones you're interested in. But remember, in C++, your program text that goes to the compiler is not just what you see in your file, it's everything that's transitively included all the way down to the bottom. So that's why when I said show me function decals, I got 337. The last few ones here were all, were all ones from my source file. So we got a constructor that matched, we have a class that matched, so on. All kinds of different things. Yes, question?
Can you make, it looks like you're in a shell for Clang.
I'm in a DOS shell. Well, it's Clang query running in a DOS
Yeah, but
window
you're
box.
in Clang query now, right?
Yes.
Same match. So can you do this from the shell so you can use correct and all these good things that said?
The answer is no, because the only arguments you can give to Clang query are the source files. The question was, can I give match directives to Clang query from the command line? Maybe I could do, let's see, maybe I could do it with -C.
Yeah.
Okay, thank you. Let's see. Yes, okay. I barely got it running and because it wasn't building on Windows, so I hadn't explored everything. It's a nice little tool for exploring the things that match. And it does, however, have a weakness, which we'll get to in a second. So is there any other kind of match anybody wants me to try before we go back? We can say var decals. So there's all the variables that are declared, and of course, you know, all of mine are at the end, and then there was just a crap ton from standard includes.
Can you do anything on templates, template arguments?
Yes, when you look at the matcher reference, you see that it is very full-featured. You can match template declarations, you can match template instantiation, you can match explicit in template instantiation, you can match template specialization. They got the basis pretty well covered, and it's not hard to write your own matcher for specific things. And any matchers that like this testing against the file name seems to be really useful and really common. And so I'll probably contribute one of those back to the Clang code. Okay, so let's go back to this. Oops, got confused. Okay, so it's very nice to be able to interactively explore the AST that way. It certainly saves a compile link cycle, which is always good. So the main place where you're going to find information about matchers is on this AST matchers reference page. And if you get interested in C++ refactoring, as I was evaluating different refactoring tools, I created what I call a refactoring tool test suite, where it's just a bunch of source files with comments identifying each test case and with an expectation of what should happen. And you find that rename is really interesting if you want to broaden rename to be more than just renaming local variables, but renaming any identifier. Yes?
Are the preprocessor tokens at all represented? Is that pointed to anyway in the AST, or is that totally obliterated?
So the question was, is knowledge of preprocessor expansion available to you when you're looking at the AST? And the answer is yes. It's obviously not as easy as just looking at the syntax tree node, but the syntax tree node is glued back to, there's a way to say, did this text come from something that just appeared in the source file, or did it come from a macro expansion? If it came from a macro expansion, what macro did it come from? And there's also, I mean, the kinds, in C++, the kinds of refactorings that we want to do, there are also refactorings that are specific to macros. Like myself, if I find macros whose macro arguments begin with double underscore and I'm not the standard library implementer, I want to rename those because the standard reserves all identifiers beginning with double underscore. So me having my macro argument name begin with double underscore or my macro name beginning with double underscore, that's bad. I want to refactor that. But refactoring the macro argument is relatively straightforward. It's a string replaced within a local context. Refactoring the macro name, now I got to make sure I get every use of that macro in all my source files, header and CPP. So in this test suite that I put together, there's like some 500 test cases in there for all kinds of different refactorings. Mostly this is what I use to test against a vendor's implementation of a refactoring tool when they said, ours doesn't have any bugs. And then I found 300 by applying this test suite. So it's full of corner cases, but it's also full of a lot of things that are important, like, you know, why should renaming a namespace be any harder than renaming a variable? The only thing that makes it hard is manually finding all the uses of that namespace identifier. But Clang knows where they all are. Clang can go find it for me and fix them. I've also, over time, accumulated some write-ups of refactorings that I think are useful to C and C++ developers, and I've written those on my blog. And so there's still room for improvement in this process. I mean, you quickly saw how it didn't take much code to get a basic refactoring tool going, and I'll show you my more elaborate implementation where I have you know, static cast and reinterpret cast and pointer to member function and pointer to function and void star arguments passed around or return values, all those kinds of things. I have a lot more of them handled, but still room for improvement here with what Clang is giving us because the packaging is not uniform across platforms. I shouldn't have to build Clang myself. It'd be different if it was a 5-minute build, but it's 90 minutes of, you know, generating lots of heat into my lap. That's not what I want. And we need a build. We did a kind of a cheat where we took our tool and we just kind of dropped it in Clang's tree and leveraged their build recipe to just kind of get our tool going. That's fine for prototyping, but we need examples of a build recipe that will work and build your tool outside of the Clang tree using only the distributed build that Clang makes available. I could not find any documentation on the grammar that is accepted by Clang query. That makes it hard to use. And just even manually navigating that AST matchers page could use some improvement. I thought of like, you know, wouldn't it be nice if just a little JavaScript application that as I just clicked on types, it just kept showing me where I could go from there and kind of construct it up interactively, a little query that I could then go and take to Clang query and try it out. That would be cool. There's enough information about the compatible types there that shouldn't be difficult. There's so far, nobody's written any kind of tutorial for how to take this refactoring tool that you've made and plug it into some kind of IDE. There are example macros that for VI, or Vim, I guess more properly, that hook in Clang format. So you get a short key sequence that you can invoke to reformat code from inside VI. But no example of saying, hey, I'm just in this source file in Vim, and I noticed right here I've got a thing that removes CStir calls could get rid of. Let me just invoke that right away. There's no example of that kind of IDE integration. And that's just for Vim, right? Which is just going to be a macro to shell out to a command and then refresh the source file. It's more difficult to glue it into Eclipse or does Qt Creator have any kind of plug-in ability?
Yeah.
So, you know,
And, um,
there's something.
you
Some
could-
way that it can be extended. So I think that once we start getting some command line tools that work, that's the next step, is to getting it plugged into everybody's workflow. And I think this is an exciting thing to work on. It's useful to the whole community. It's one of these things where we can all make our own lives better, kind of stone soup wise. We each put one little ingredient in the pot, and the next thing we got a tasty soup. Just here at the conference, I realized Clang Modernize needs a new feature, and that is if your class derives from Boost non-copyable, we should delete that and replace it with a deletion of the copy constructor and copy assignment, right? We should that's what it means to be non-copyable. So in a C++11 term, so we should have a enhancement to Clang Modernize that does that kind of a transformation. I think that would be cool. I think we can all think of little things that are, remember, refactoring is transforming the structure of existing code while preserving the same behavior. Obviously, rename is a behavior preserving transformation as long as your new name is not conflicting with any existing name. And as long as you get all the uses of the old name modified. So if there's anybody that's interested in collaborating on that, I would love to hear from that. So just to recap, all the hard stuff is done for us by Clang. So if you ask a vendor for a feature for refactoring in your IDE or anything, and they're like, it's C++, it's so hard to parse, you just say, go get Clang and stop whining about that. Just get on with it. We got started by copying an existing tool. It's important to build a set of source test files that you feed to your tool to keep double checking yourself along the way, kind of test-driven development with the source file being an acceptance test for what your refactoring tool is supposed to do. Start with simple matches against the AST. Build appropriate replacements. Incrementally extend and refine your matching to get it handling more things. Use Clang Query to go and prototype matchers. And if we all chip in a little bit and start building some tools, I think we can get things really moving forward. Let's take a look at my final, well, not final because I'm still working on it, but I can show you where my little remove void star remove void has gotten to. So here's my final guy. That's way too small for you guys to see, sorry. Let's fix that. Get rid of this. Can you read that? So I'm matching function decals where the parameter count is 0. I'm matching name decals because I need to match variables and other names that can be, named decal ends up being needed to handle type def. I'm matching fields, variable declarations. I'm looking for C-style cast expressions, static cast expressions, reinterpret cast expressions, const cast expressions. I added explicit cast in there, but I think it might be unnecessary for given all the other ones that I have in there. My little test file has grown. I've got functions with some white space thrown in, function declarations, function definitions, a class where the constructor and destructor and member functions had void in the argument list, pointers to functions as class members, pointer to member functions as class members, pointer to functions as just declarations, pointer to functions that are declared and defined with an initializer. I want to make sure that I don't get rid of that initializer. I don't want to take correct code and turn it into incorrect code. Type defs with strange white space shoved in there. Global declarations of pointer to member, declaration with an initializer, a type def of pointer to member, functions with local variables that have pointer to function, member functions with local variables that are pointer to member function, and on and on and on, right? I just keep adding more crazy, disgusting stuff into this file as I think of it. Yes, question?
Going back to the previous slide, or previous file, the actual code, can you remind me again what the bind?
So when I'm using the same callback for all the matches, and when I match a node, I bind it to a symbol so that I can say, go get me the function decal node that was bound to fn.
So that fn is just a thing you invented.
It's just a name. Yeah, all those strings in the bind arguments are all just names that I use. And the backside of it is, let's get up here. The backside of it is that I say, go find me the function decal that is bound to fn. So this is the only other place where fn is used.
Okay.
And you might think like, yeah, but you're only binding to one function decal, so why even give it a name? But I could be interested in multiple flavors of function declarations. I bind them to all the different symbols, and then when I'm inside here, I can fetch them all and be able to distinguish between each one. And as you can see, I have this, modifiable file thing that I'm using. And then I basically, once I identify which case I'm handling, I just delegate to a member function to do the real work. The member function is pretty similar to what we saw before. We said we get the text. Is it a declaration? If it ends with void argument, then go ahead and build a replacement. And this ends with void argument is where I handled white space. That's how I got the crazy white space to work. So we can see this run. So here I am with my test file with all that crazy stuff in it. I have it under version control, and we can see that it's not modified. I can run ran my test, check the status. It says I've modified the file, so we can go over here to look at a diff, and I probably need to make these fonts bigger. Where do they put it? Options, file viewer, where's fonts? Oh, I see. Thank you. Pair programming, yay. Okay, so now it's bigger. Let's see if we can get a little more on there. So you can see it took all the voids out of these declarations. I lost some white space. That could be considered a bug or not, but at least I haven't made the code incorrect. Took the void out of these definitions, took it out of all these member declarations, took it out of the pointer to function and the pointer to member function, took it out of these variables that are pointer to function, or whether they're initialized or not, and I preserved the initializer, took it out of this type def and this type def. These pointer to member functions, they also got fixed up. This type def of a pointer to a member function also got fixed up. These local variables inside a member function. There's only one in here that I am not yet handling properly, and that is this one. Thank you. And that's pretty much it. Is there any questions on any of this stuff? Hopefully you can see that it's not as hard as you might have been thinking. And you may have now incentive to go fix a problem that's been nagging you in your code base, but you didn't want to do it because you'd have to manually edit thousands of files. Yes?
So I suppose nothing stops you from running Clang to refactor, but still using a different compile to...
Yes, the question was, nothing here is stopping you from using Clang to refactor, even if Clang is not the compiler you use to build your code. And that is totally correct. There is a Visual Studio bolt-on that somebody created that lets you run like Clang format, but you're not using Clang as the compiler. Yes?
I think what you still should mention is that there is in the tool extra directory a tool template where you could get started with.
So the observation was that there's a template for a starting point on a tool in the tools extra directory in the Clang distribution. The problem is if you get the pre-built package, you don't get that template. It's only in the source tree, but yes, it is there. I found it was better to start with remove cstir calls because it already was doing something and I could just swap out the behavior and it was obvious to me where to swap things out. But it's a good point. I would like to see some kind of, project wizard or something where you say, what's the name of my project and what's the name of the source file, and it uses a template to generate out a starting point for you with some to-do comments saying, you do this here and then do this over there. I think with an out-of-build tree build recipe, that would be immensely useful in getting people going even faster than it is now. Any other? Yes, we'll go you and then you.
Do you consider using this technique to do code completion?
So the question was, can you use this technique to do code completion? And the answer is there is special support in Clang to supply code completion, and I believe some people have glued that into Vim as an example, that you can use Clang to do code completion. Code completion is a different thing from refactoring, because in code completion I'm creating code, but there are facilities to do code completion in Clang and assist with that. Because Clang has all the knowledge of all the, if I have an object and I type -greater, Clang knows all the methods on that object that could be called, so it can supply me with a list. And that is a use case they're very much aware of, and they've built specific tooling to support that. Yes?
Yeah, does Clang support some kind of plugin? So could I write my refactoring tool as a little DLL or a dynamic library which I load into Clang and then run it? So I could imagine
Yes.
that kind of database. So if I have a big project in my company and then I want to create that build database with all those comments we don't use CMake yet, unfortunately, and I would like, since we are using Clang already through Xcode, I would like to just put in a plugin instead of compiling the code, I refactor the code kind of.
Okay, so the question was, does Clang have some sort of plugin API that I can use to instrument my build and capture all the compile commands, for instance, in order to build this compilation database? And the answer is yes. There is a well-defined plugin mechanism for Clang where you can plug in on the front end. You can also, because the whole compiler is available as a library, you can build your own front end that does custom processing and then sends it off to Clang. So there are a lot of options. It is a rich environment where you can plug in many different spots. I like this, for a refactoring tool, I like this approach because I don't need to worry about how to launch the compiler or what the build command is. All those things are all just kind of taken care of for me. I can just focus on writing the code that says, find this, replace it with that. But it is very extensible. You can plug in many different ways. Yes?
So the find all the matches, replace it seems like it would work really good for lots of things. But like, my favorite refactoring is the extract method. It doesn't seem to really match that model. Like, is there a different model, or what are your thoughts on how to do it?
So it does match that model, and here's how it would. In extract method, you have a source location representing your starting point and a source location representing the ending point. So we had a node and queried for the source location. You can make the inverse query. Given a source location, what syntax node matches that, and walk the tree backwards and forwards to adjacent nodes. And you would have, in the case of extract method, there's a little bit of flow analysis you have to do to identify what things are coming in that need to be turned into parameters to the extracted method, and how are things coming out. Generally, the Visual Assist X, for instance, has an extract method, and it's pretty good as long as nothing's coming out. It gets very confused on things that come out of the block that I'm extracting. So you can do that analysis, and then you could apply that refactoring, fix up the flow to make sure everything was still correct, and then you'd be good. It gets even more wrinkly, right? Because I could be inside a global function and I'm extracting, in which case that has to be extracted to a function. If I'm in a const method and I extract, the new method has to be const. If I'm in a regular method and I extract, then it can be extracted regularly. But if I extract the new method, should the new method be public, private, or protected? There are many choices, and there's no one right answer to a lot of these things. But just getting started of having a reliable extract method would be a big win. And I hear via Chandler's talks that are recorded, so I'm not putting words in his mouth, they have lots of internal refactoring tools at Google. I wish they would share them, but if they won't, then we're going to have to make them.
Oh, just look at GitHub. You find a bunch.
I've found some stashed away in some. When I said I was going to give this talk, some people emailed me and say, here's another example I've got. And I'm like, okay, it's kind of hidden away in a random GitHub repo. And it wasn't even discoverable by browsing, so I wasn't sure if I could share that or not. But I think what we need to do as a community, or what I'd like us to do as a community, is to start getting a central repository. Maybe Boost Incubator would be a good place to kind of, it's not really a library though. But anyway, I think we can move forward at a much faster rate if we all contribute in, and then we all, so I write one little thing and that we all get to use it, and somebody else wrote a little thing, and 10 people write 10 little things, and I got 10 little things I can use. I think that is really the answer. Any other questions? I got 5 minutes, so we got time.
I have one remark or a comment. I did a similar talk at Meeting C++ 2 years ago. And if you look at Google for Clang lib tooling and Qt Creator, you will find my German blog entry from 2012, where I read a little bit about how to get a refactoring tool built with Clang, running in Qt Creator, compiling with Qmake. It's 2 years old, I don't know if it's still
So you built the tool with Qmake?
Yes.
Yeah, okay. Yeah, I'll go check it out because
I had to go that maybe I wanted to use Qt with it, and it worked.
Yeah, now we used a bunch of stuff from Clang and we kind of stole their little build environment. But fundamentally, you're just using headers and libraries, and you could use that from any build environment. It's not specific to CMake. It's just that that's what they were using, so it was the easiest way to just hijack something for our own purposes. That is one of the very nice things about this, is that it is a library that is designed to be used in this way, so it is documented. The Doxygen information is good on all the abstract syntax tree nodes. There's also documentation on how to hook into the preprocessor at that level if you need to do that. I haven't done that yet. It's scarier, but maybe for next year, I'll show you how to do that. So for me, I was just like, hey, Chandler, I watched that talk. It seemed like it was easy. Let's just go try it and see how easy it was. And I got a guy on my team that does the void thing all the time. So I was like, let's just try this, and then we can see if we can just fix all the code at once. And then if there's no existing instances of this old bad habit, you're less likely to have new people putting more instances in, right? Because you tend to add code in the same flavor and style as the code that's there. Yes?
The ultimate thing to do is to hook the refactor tool to your source code control check-in. And every time you check in a file, it runs the refactor tool and at least says, hey, you put a void thing, you put a C style cast, you did something dumb, don't do that.
So the comment was you could hook these refactoring tools to your commit mechanism to prevent new instances of this bad style from creeping in. And you should read the Clang developers mailing list, because people contribute patches and like, hey, yeah, this all looks great, just run it through Clang format before you submit. And that just kind of vaporizes all their white space differences. This could be, a similar kind of thing. I think maybe on occasion I might have even seen people say, great patch, just run it through Clang Modernize first, because you're doing some things kind of the old way. Any other questions, comments? Okay, we have a little bit of time, and I have a little bit of swag left.
I have one question.
Yes.
Can you generate code?
Well, the question was, can you generate code? So generating code is inserting nodes into the AST. You can do that. Of course, an example would be if your refactoring was extract method, I have to touch up the header at a minimum. I may have to touch up a CPP file, and I certainly again need to find some way of inserting text, inserting nodes into the AST and supply the associated source text. It's a more advanced operation, but yes, that is all possible. In other words, the syntax tree that you get back is modifiable, but it is also dangerous because you can take a syntactically correct syntax tree and then modify it to be nonsense, right? So,
If you need an example of that, you can go into the Boost Modernize code base, and then you have some examples in there.
yes, Clang Modernize does exactly that.
Whatever it is.
I mean, I could bring it up after I got the whole tree on this laptop. I could show you, but there are examples of, it's just more complicated than I want to go on. So I have a couple CDs of 3D graphics demos and a couple CDs of electronic music. I'm just going to let you come up and grab one if you're interested. And that's basically it. Thanks very much for your time.